Hello and welcome to another video for Calculus 1. In this video, we are going to discuss about definite integrals. So the first thing that we are going to look at is the difference between net sine area and total area. So for example, if we have a graph, let me draw a graph here. So let's say we have this function here, f of x. Now let's say this is a sub 1 and this is a sub 2. So the area above the x-axis, so let's say this is y and this is x. So we consider the area above the x-axis as positive area, okay? And then area below the x-axis and above that curve. So area between the curve and the x-axis, that's what we are looking at. So this area, we consider this as a negative area. So this is the first one. Here we have a positive area. So this is positive area and this is negative area. So when we say the net sine area, it is the net area. So A1 minus the area below the x-axis, which is A sub 2. So that is the net area. But when we say total area, we find the sum of those two areas. So A1 plus A2 gives us the total area. So this is similar to when we talk about distance and displacement. So net sine area is just like displacement, and then total area is like distance, okay? So now we have in past several videos, we talked about the Riemann sums, we talked about left Riemann sum, right Riemann sum, and midpoint Riemann sum. Now we are going to talk about the general Riemann sum. Okay, so here it's the same process. We have a function f which is continuous and is defined on the closed interval ab, and then we divide that into n subintervals with all of that condition. Now the difference between the left Riemann sum, right Riemann sum, and midpoint Riemann sum, and the general Riemann sum is when we did the left Riemann sum, this x sub k star, this point which determines the height of the particular rectangle. For the left Riemann sum, this was the left endpoint of that interval. For right Riemann sum, this was the right endpoint of the interval. For midpoint Riemann sum, this number was the midpoint of that interval. Now, when we say general Riemann sum, we can take any point on that interval to determine the height of the rectangle. So it doesn't have to be left, right, or midpoint. It can be any point on that subinterval. So when we construct rectangles in that way and then take any point on that interval to determine the height of the rectangle, now that sum, that Riemann sum becomes the general Riemann sum. Okay, so it's the same thing. Instead of saying left, right, or midpoint, we are picking up any point. It could be left, it could be right, or it could be midpoint, or any other point on the interval. So that's the difference here. And again, when we talk about the general Riemann sum, it doesn't have to be the uniform length of the rectangle. The width of the rectangle could be different. Okay, so that's the Riemann sum, general Riemann sum. It's very similar to what we did in the previous video. So this is what we are going to look at now, the definite integral. Okay, so the definite integral, the definition is if f is a continuous function on the closed interval ab, the definite integral of f from a to b is given by, or we denote it by, we use this notation right here to denote this one. So from a to b of f of x dx, okay, and that is equal to, so this is the general Riemann sum, or any Riemann sum, and then we take the limit. So in the last example, in the last video, we evaluate the true area under the curve using this formula right here. Now that is what the definite integral of the function f of x from a to b is. Okay, so in other words, this integral here, that gives us the true area under the curve and above the x-axis. So here I have put a note here. So this definite integral, it gives us the net sine area. It does not give us the total area between the curve and the x-axis. Okay, it gives us the net area. So it's very important that we understand that. Okay, so any area below the x-axis is going to subtract, any area above the x-axis is going to consider that and as positive, and below the x-axis as negative. So it's going to find the net area under the curve. Now there's a theorem when is a function integrable, or when we can integrate a function, or when we can find the definite integral of a function on any interval AV. So it is this is the condition. So f either it has to be continuous or it could be discontinuous, but the number of discontinuity should be finite. So finite number of, if we have finite number of jump discontinuity, and then we can consider that function as integrable function in the given interval. Okay, so just to illustrate this thing in a graph, this is what it means. So if we are finding the area from A to B, okay, let's say whatever the B is, let's say here, this is f of x. Now what we just do is we'll just take the integral of that function f of x from A to B, and then it gives the net area. So it will take this area as positive, this area as negative, take the difference, and it gives us the net area between the curve. I mean, between the curve and the x-axis, okay? So now, using the definition of definite integral, we are going to evaluate this integral here, definite integral. And later on, we'll in the next section or next video, we'll talk about the fundamental theorem of calculus, which allows us to find this integral, definite integral, in much easier way. Okay, so but now we are going to use the Riemann sum, the definition, and we are going to evaluate this definite integral. And another word is same as saying finding the net area under this curve is what the definite integral is. Okay. So let's go ahead and do this. So first we are going to find the Riemann sum, and we are going to take the limit n approaches infinity, and then we'll evaluate the definite integral. So when we are finding the Riemann sum, first thing we are going to find delta x. So we're going to use the right Riemann sum. This is very important. You can use any Riemann sum, but in this question we are using right Riemann sum. So the first thing is delta x equals b minus a. So this is b, this is a. So 4 minus 1 over n. So we don't have any n, particular n here, so we'll just consider that as n. And at the end, we are going to take the limit, okay? Now this is equal to 3 over n. Now if you remember the next thing, I gave you the order of the procedure that we do here. We find delta x, then we will find x of k star. So this point that determines the height of the rectangle. Okay, so that is given by, for right Riemann sum, it is given by a plus k times delta x. So here a is 1 plus k times delta x is 3 over n. So which means we have 1 plus 3k over n. Now the next thing is we'll evaluate this function at x of k star. Okay, so we'll find the value of the function, which is x squared minus 1, which means we have 1 plus 3k over n squared minus 1. Now when we expand this, we get 1 plus 6k over n plus 9k squared over n squared minus 1. So 1 minus 1 is 0, so we will get 6k over n plus 9k squared over n squared. Now we will use the formula for right Riemann sum, which is, let's say, r sub n equals the summation from k equals 1 to n, and then our function, the value f of, so let me write the formula first. So it's f of x k star delta x. So it means summation k equals 1 to n. So this quantity is right here. So 6k over n plus 9k squared over n squared times delta x is 3 over n. So let's go ahead and distribute this. So k equals 1 to n. When we distribute that, we get 18k over n squared plus 27k squared over n cubed. Now let's go ahead and separate this, and let's do one thing. So here we are summing over k. That means n is a constant. So we can factor out constant when we are finding the sum. So what I'm going to do is I'm going to do two things here. I'm going to factor out that constant, and also I'm going to separate this sum. So this is what I'm going to do. So 18 over n squared, then summation k equals 1 to n, and then k here, plus 27 over n cubed, then summation k equals 1 to n k squared. So the first one is the sum of the first k natural numbers. So we have looked at the formula for that summation, and I'm just going to write it here so you can go back and refer those formulas. So the formula for this one is n times n plus 1 over 2. That gives the sum of the first n natural numbers, okay? Now plus 27 over n cubed, and we have seen that formula as well. So this is the sum of the squares of first n natural numbers, so which is n times n plus 1, okay, times 2n plus 1 over 6. Now let's go ahead and simplify this. So here we have 18 over n squared times, so if you multiply here, so we get, sorry, this is 18 over n squared, it's not 18n2, okay, so n squared, and then when we multiply this, we get, so we can also do this, let me erase this. So we can cancel out here, 2 goes to 9 times, let's write it this way. So we get 9 over n squared, then if you multiply, you get 9 squared plus, sorry, n squared plus n, plus here also we can cancel out some of these things. So what we can do here is 3 goes 2 times, 3 goes 9 times. So which means we can rewrite this as 9 over 2n cubed. And then let's go ahead and multiply this. So when we multiply this, and so you can multiply this, okay, so I'm going to write it, the final expression that I have here. So 2n cubed plus 3n squared plus n. So you can multiply. So n times n is n squared times 2n is 2n cubed. And then you can distribute and combine the like terms. Okay, I skip those steps because I don't have a lot of space here. So now the next thing that we are going to do is, so keep writing this, r sub n equals. So now when we distribute this here, okay, so if we distribute this over here, we get 9, because 9 over n squared times n squared is just 9, plus we get 9 over n when you multiply this one over here. And then when we distribute here, 2n cubed cancels out, so we just have plus 9. And when we distribute this over here, we get 27 over 2n, so plus 27 over 2n. And then when we distribute this to the last one, we get 9 over 2n squared. So plus 9 over 2n squared. So that is the Riemann sum that we have. So let's just clean this up a little bit. So we have r sub n equals 9 plus 9 is 18, plus, let's write 9 over n, plus 27 over 2n, plus 9 over 2n squared. Now the definite integral is given by the limit of this Riemann sum. So we can write, therefore, we can write this as, so we have integral from 1 to 4 of x squared minus 1 dx equals limit n approaches infinity of r sub n, which is limit n approaches infinity of 18 plus 9 over n plus 27 over n plus 9 over 2n squared. Now when we take this limit, as n approaches infinity, 9 over that n is, that approaches 0, because 9 divided by a very large number. Similarly, 27 over, this is 2n, sorry. So that goes to 0, and 9 over 2n squared, that also goes to 0. So which basically means this integral equals 18. So in another word, to say that the area under the curve, the net area under the curve x of x squared minus 1 is 18, or the definite integral of x squared minus 1 from 1 to 4 is 18. Okay, but this is a long way to do it, but that's what the meaning of this definite integral means. But later on in the next video, we'll learn about how to do this in shortcut, or how we do this in like 2 or 3 steps. Okay. So now, as we said, the definite integral is just the net area. So what we are going to do next is we are going to graph these functions, and we are going to use the graph, and we are going to interpret that in terms of area of certain figures or shapes, and then we are going to find the definite integral. So first thing, you can take out your calculator and you can graph this one. So this is a semicircle. So the graph of this function looks like this. So if we draw the graph of this function, okay, so it is going to look, let me go ahead and draw this. So this is a semicircle with radius 2. So if you look over here, the x-intercepts are -2 and +2, and the y-intercept is 2. So it is a semicircle like this. Okay, doesn't look like a semicircle. My figure is not that good, but this is a semicircle. So basically what we are doing is we are finding the area of this semicircle. So we know the area of the circle is pi r squared. Okay, that's the area of the circle, but we are looking at the area of semicircle, so that becomes 1/2 pi r squared. So now this definite integral that we have here from -2 to 2 of this function 4 minus x squared dx equals the area of the semicircle that we have here. Okay, which means 1/2 of the area of the circle, that is 1/2 pi times radius is 2 squared, and that gives us 2 pi. So that is the area of that semicircle, or that is the value of this definite integral. Now let's look at another one here. Let's go ahead and graph this function. The graph of this function would look like, let me draw it over here. So that does not look like a straight line. So this is a line with negative slope, and if you look over here, x-intercept is 2 and y-intercept is 2. So probably the graph is going to look like this. Let me draw a little bit different graph. 2 is small space here, so let me draw it over here. I want a straight line. Come on. Okay, so this is 2. This is also 2. Now we are going from -1 to 3. Let's say 3 is right here. And then let's say -1 is right here. So what we are looking at here is the area from -1 to 3. So we're looking at this area. So basically what we are looking here is we have two triangles. Here's one triangle up here, and there's another triangle down here. So the definite integral that we have here from -1 to 3, 2 minus x dx equals to the area of upper triangle. Let me write triangle this way, okay? It's not a delta, so if you don't get confused, I'm just writing that as a triangle, minus area of lower triangle, okay? Because the definite integral is the net area, so area above the x-axis minus area below the x-axis. So this is x-axis and this is y-axis. So let's go ahead and find the area above the x-axis. So for this triangle here, okay, so for that triangle, the base is from -1 to 2, which is 3. The height is, we evaluate this function at -1. So what you're going to do is you're going to do 2 minus, replace x with -1, and that gives us 3. That means the height of the triangle is 3. So always the height is given by the value of the function at that x value. Okay, so height is 3, base is 3, so area of the upper triangle is 1/2 base times height, minus the area of the lower triangle here is, now the base of that lower triangle, so we can consider this as base, so which is, we go from 2 to 3, so this is 1, and this is the height. So the height of the triangle is, we plug in 3 into our function, so 2 minus 3, which is -1, but it's a height, so we consider that as a positive number. So 1/2 times base is 1 times height is 1. So this is 9/2 minus 1/2, which gives us 8/2, and that is 4. So therefore, the definite integral from -1 to 3 of 2 minus x dx is 4. Let's look at more examples. So now we have a absolute value function here. So usually the absolute value function, the integral of absolute value function gives us the total area because we are just looking at the absolute value or the positive values only. So let's go ahead and grab this function again. We are going to grab that. Okay, so now we are going from 0 to 3, okay? So the y-intercept of this function is 6. So let's say 6 is right here. The x-intercept of this function is 2 right here. So it's absolute value function. So this is going to look like this. Okay. Now we are going from 0. This is 2, but we are going to 3. So we are looking at this area. So the area that we are looking at here is this area of this triangle, and area of this triangle right here. So let's look at the first triangle. So the base of the first triangle is 2 because it's from 0 to 2. The height is 6. Now for the second triangle, the base is 1. The height is, let's go ahead and plug this into our function. So it is 3 times 3 minus 6, which is 9 minus 6, and that is 3. So the height of this triangle is 3. Now, the definite integral is given by the sum of those two, area of the sum of those two triangles. So the definite integral from 0 to 3 of absolute value of 3x minus 6 dx equals sum of the area of those two triangles. Okay, so I'm just going to find the area here. So it's 1/2. The area of the first triangle is 1/2 base times height. Okay, and then plus, we add them here because both areas are above x-axis. So 1/2 base times height. And that gives us, so this is 6 plus 3/2, and which is 15/2 or 7.5. Okay. Now let's go ahead and look at the next one that we have here. So we have 2x plus 5. So this is again a line. So let's go ahead and grab this function. So the y-intercept is 5 and the x-intercept is -2.5. So if you look over here, you can see that from here. So it looks like this. Okay. So we are going from 2, let's say this is 2, to 5. Let's say this is 5. So what we are finding is we are finding this area from 2 to 5. So we are looking at this area. Now what we can do here is the base, this length from here to here is 5 minus 2, which is 3. Let me use a different color for that so that you don't get confused. So this is 3. Now this height here is, if I take 2 and plug it in here, so 2 times 2, 4 plus 5, so the height here is 9. and this height here is, if I take 5 and plug it in here, so 5 times 2 is 10, plus 5, 15. Now actually I can do this in two ways. So let me do the first way. The first way is I'm going to divide this region into two parts. So if I draw a perpendicular from here to that line, so we have a triangle and a rectangle. So for that triangle, the base is still 3. This height is, so total is 15 minus this height is 9. So 15 minus 9, this height is 6. So what I can say here is the definite integral from 2 to 5 of 2x plus 5 dx is the area of the triangle, so area of the triangle plus the area of the rectangle, okay? So it means the area of the triangle is 1/2 times base is 3 times height is 6 plus the area of the rectangle is 9 times 3. 9 times 3. And that gives us, so this is 9 plus 27 and it is 36. Now another way to do this is the whole thing is a trapezoid. So we can just find the area of the trapezoid. So from 2 to 5, so this is another way, okay? So I'll just write or here. You can either do this or you can do this, okay? So 2x plus 5 dx equals the area of the trapezoid, which is 1/2. So the area formula is 1/2 times height times a plus b, means these are the length of the parallel sides. So here the parallel sides are this one here and this one here. So these are the parallel sides. So we have 1/2 times, now the height is this, okay? This is kind of like vertical trapezoid now. So the height is here, which is 3, times sum of the parallel sides, so 9 plus 15. Okay, so that gives us 3/2 times 9 plus 15 is 24, and that gives us 36. So this is another way to do it. If you remember the formula for trapezoid, you can do the second way, or you can just divide into two parts and you can just do the first way, okay? So now, so that those are some of the examples using the area to find the definite integral. Now let's go further with this one. So similar example here, we are given the graph, we are already given the area of the region. So here it means from A to B, this is the region, and the area is 5. So when we go from B to C, so this is the region below the x-axis, so the area is 8 for this one. And then when we go from C to D, the region is right here, this region, the area is 4. Okay, so when we write the definite integral, from A to B, so from A to B, f of x dx equals this area, which is 5. Now from C to B, so when we go from C to B, remember when this is C to B, but this area 8 is from B to C. So when we go from C to B, what we need to do is we need to change this one, okay? So it's the opposite. So we put a negative and then, sorry, there's no that question. I was thinking of different question. It's still from B to C, sorry. So B to C is, the area is 8, but we are looking at the net area, which means below the x-axis, the area below the x-axis is negative. So this is negative 8, okay? Now going from A to C. A to C is, what we do is, we can split this as from A to B and B to C, or area above the x-axis is positive and area below the x-axis is negative. So it is 5 minus 8, and that gives us a net area of -3. Okay. Now the next one, we are going from A to D. So when you go from A to D, okay, so A to D is 5 minus 8, then plus 4. So we add the area above the x-axis and we subtract the area below the x-axis, and that gives us 1. Now, look at some property of the definite integral. So if we integrate any function from a to a, which means you have a function, you are going from a to a, that means there is no region, no area, so the area is 0. So that's why the definite integral going from a to a f of x dx is 0. If we have a to b f of x dx, then if we switch this limit, if we switch them, then that becomes a negative integral. Okay, so negative of b to a. So if we switch this, then the third one is the integral of sum of two functions is equal to the integral of those functions, and then we can add them. Or if we have subtraction, we can subtract them. Okay, and then if we have a constant multiple, we can always pull that out. And this one is number 5 is, so for example, if we are finding the area under the curve from A to B. Let's say P is any point here. So if we are finding the area under the curve from A to B, we can find the area under the curve from A to P and find the area under the curve from P to B and add those two. That's what we are doing here. Okay, so we can go from A to P plus P to B. Okay, it's just splitting that into two parts. This might be useful when we have some discontinuity. For example, if the function is discontinuous here, okay, and then what we can do is we can calculate the area from A to B and A to P and P to B to find the total area. So now we are going to use those properties here. The first one, so this is what's given here. We are given the integral. We are not given the function. We don't know what g of x is. It might be a square root function. It might be quadratic function, it might be some exponential. We don't know what that is. Okay, so what we are doing here is we are just given those two values, and based on that we are going to find the values, and some of them might be possible to do that. For some of them we might not have enough information. Okay, so let's go ahead and see which we can evaluate and which we cannot. So the first one is going from 0 to 8. So we have 0 to 8 is given negative 15, and we have 5 times g of x. So using the property of constant multiple, we can bring that 5 out, and we can write 0 to 8 g of x dx. And we know that this is given to us, 0 to 8 g of x dx. That integral, definite integral, is negative 15. So this value equals negative 75. Now the next one is given that 3 to 8. We are asked to find the definite integral of g of x from 3 to 8. So it is just like, so we have this, okay, so we have from 0 to 3, and then we have 0 to 8. So 0 to 3 gives the area from 0 to 3. And then 0 to 8 gives the area from 0 to 8, the whole area. Now what we can do is, to find the area from 3 to 8, we can subtract 0 to 3 from 0 to 8. So we are taking off that part from the whole thing, okay? So if we do that, so we can rewrite this as, so the definite integral from 3 to 8, we can rewrite this as the definite integral from 0 to 8 of g of x dx minus the definite integral from 0 to 3 g of x dx. Okay, so if we do that, then we know that, sorry, what happened? So we know that the first one is negative 15 minus the second one is 6. So that means we get negative 21. Okay, now let's see what we have. The next one is, so we are given the area from 0 to 8, and we asked to find 8 to 0. So first let's go ahead and factor that 4 out, or we can write this first. So we know that we have 0 to 8, so we cannot find 8 to 0, but we can change this one and we can write negative of 0 to 8. Remember this property here? If we switch this limit, okay, if we change a to b into b to a, then we have a negative. So negative of 0 to 8, so 4 g of x dx, and then we can factor that 4 out, so we have integral from 0 to 8 of g of x dx, and then negative 4 times, so 0 to 8 g of x dx, that's given negative 15, so that gives us 60. Now for the last one, it's a little bit different. We have the absolute value, okay? to find the area from 0 to 8. Now we are given the area from 0 to the net area from 0 to 8 is negative 15, but that does not mean taking the positive of this one would give this one, because we could have some area above the x-axis and some area below the x-axis. So this one just gives us the net area. So it takes all this positive and subtracts negative. But this means we take this all positive area. We make this positive and we add all of them. So just with the given information, we won't be able to figure out what is this. Okay, so we need more information. We really need to know what the function is, or we need to see the graph. If we are given the graph like this one here, the previous example we looked at here, this one, then we'll be able to find that. Otherwise, we won't be able to calculate that. Okay, so here we will just say that this is not possible, or we cannot find this with just the given information. So there's not enough information given to us. So we'll just stop here. So in the next video, we're going to talk about how to evaluate the definite integral in more efficient way, that is using the fundamental theorem of calculus. So I'll just stop here. I'll see you again in the next video.